All right, building a box cost problem. So one use for optimizations is to build a box to a certain specification, but yet still have it be the cheapest possible. All right, so here we have our box. Of our box, the four vertical sides will be silver painted, all right, costing $5 a foot squared to paint. The lid and base will be gold painted, costing $8 a square foot to paint. What we need to do is find the dimensions of the box that is cheapest to make, but contains 12 cubic feet of volume and has to be 2 feet high. All right. So we know that the height here will have to be 2 feet, and then this is the width, and this is the length. Okay. So now let's figure up our cost. All right. We know our total cost C. Okay. Okay. This is going to be the front side. We know that's going to cost $5 times whatever the area of the front is, plus $5 for whatever the area of the back is, okay, plus $5 for the area of the right side, plus $5 for the times the area of the left side, plus, okay, so that takes care of all of our vertical sides. Now our top, it's going to cost $8 times the area of the top, plus $8 times the area of the base. I'll call it base instead of bead to not confuse it with the back. All right. So here's kind of our generic equation. Now we need to simplify that down into something that's a little more usable. All right. So cost equals 5 times the area of the front. Well, what's the area of the front going to be? Well, here's the front. Well, it's going to be the height times the length. Well, the height is 2, so the area of the front is going to be 2L. Plus 5, the area of the back is also going to be 2L. Plus the area of the right side, which is going to be 2 times the width, so it's plus 5 times 2W, plus 5 times 2W again for the left side, because the left side is going to be the same, plus 8. Now, what's the area of the top? Well, the area of the top is going to be length times width, plus 8 times length times width again. All right. So now if you simplify all this down, you're going to get 20L plus 20W plus 16 length times width. So this is our first equation that we're going to need. All right. What do you think the second equation that we're going to need is going to be? If you said volume, you are correct. Volume equals length times width times height. So in our case, it has to be 2 feet high. So our volume is going to be 2 times L times W. But we also know that the volume of our box will have to be 12 cubic feet. So we know that 12 equals 2 times length times width. Okay. Now, remember how we were solving for variables, single variables and things like that? We want to try to get some of these variables out of here so we only have one variable so we can actually solve for one of the variables. Because once we get one of the variables, we can easily find the other one. Well, if we divide both sides by 2, all right, let me get this out of here. We know that 6 equals length times width. Well, if you look, here's length times width. Okay, so we can actually take that out and put in 6 because we know 6 equals L times W. All right, now let's solve for L so we can have all W's in our equation. So we can divide this by W, divide this by W. So now we have this solved for L. L equals 6 over W. So now what we can do is we can eliminate L from our equation for the time being. So now we know that C equals 20 times 6 over W plus 20W plus 96. All right, plus 96. Now, from here, you're still going to solve these like before. All right, you're going to have to take your derivative and then solve for W and then plug W back in and solve for L. Okay, what I want you to do for your ticket in the door, because we've done several optimization problems at this point, so you should be comfortable with optimization problems. So what I want you to do at this point, I want you to finish this out, okay? I want you to finish this out and find what L and W equals. So L equals, W equals, okay? I want you to find L and W. I'm gonna make this your ticket in the door for tomorrow. So find L and W and bring it to me in class, and I'm gonna check this in class to make sure you've done it correctly, okay? So as you can see, you can use optimizations to find a lot of different problems, to solve a lot of different problems. Examples, if you were boating and you were trying to go home and you walked at a different speed, you paddled the boat, where would you have to hit shore to make it home the fastest? Okay. Building a box, what's the dimensions of the box? That's still 12 cubic feet, but it's the cheapest to build, but it's still 2 feet high. All right. So finish this out, bring it to class tomorrow, and I'll check it. Okay. See you tomorrow.